Hi, I'm Mohammad Malikzadeh and I'm presenting our paper, DANA, Dimension Adaptive Neural Architecture for Multivariate Sensor Data. We consider sensors embedded in mobile and wearable devices, especially motion sensors. In practice, these sensors might not be available all the time, or the sampling rate of the sensor might change time to time. So the problem is how to process sensor data of variable dimensions. The reasons are we want to be adaptive to hardware faults like missing some sensors, power saving by reducing sampling rate, working across heterogeneous devices, or enabling privacy and users' control on data sharing. Previous works proposed useful deep neural networks for sensor data processing, for example for health monitoring. But all these works assume fixed data dimensions at inference time. The basic solutions are either data imputation for missing data or resampling of the data. So instead of making the models adaptive, they propose to fix the data, which brings more questions and challenges. In our paper, we show how to transform a deep neural network for being adaptive to variable dimensions. To this end, we propose a new layer that is called dimension adaptive pooling. We also show how to train such adaptive models to keep them accurate at inference time. We propose a dimension adaptive training procedure. Combining DAP and DAT together, we give dimension adaptive neural architecture. The DAP layer is located between the last convolutional layer and the first feed-forward or recurrent layer. While the inputs to a DAP layer can have variable dimensions, the output of the DAP layer always has fixed dimensions. Thus, it is consistent for processing with feed-forward or recurrent layer. We show that DAP gives better accuracy than other solutions because it captures the correlation among sensors. DAP layer has two customizable parameters, but it does not add or remove any trainable parameter to or from the model. As I mentioned, using a DAP layer makes a model adaptive, but such a model also needs to be properly trained. That is a training procedure that uses two techniques. First, after sampling a batch of data, we randomly change the dimension of the data. Second, instead of immediately updating the model on every batch, we accumulate the gradients of multiple batches and update the model with the average gradients of multiple batches. We show that helps the trained model to have better generalization at inference time. Here I present one of our experimental results. We compare 4 models. The red line shows the original model that is one of the state-of-the-art models used in previous works. The blue line is the same model but using a DAP layer. We see that it is not enough to only use a DAP layer. The green line shows when we use DANA to make model adaptive to changes in the sampling rate. The accuracy gets much better in the left plot, but in the other 2 plots in the middle and right, where only one sensor is available, the accuracy of the green line is dropped. The purple line shows when we use Dana for both dimensions, sampling rate and sensor availability. Dana outperforms other models by about 20% more accuracy. We also designed an experiment where we can control the correlation between two sensors. We see that compared to other basic solutions that are shown by the red and blue lines, our solution that is shown by the green lines gives us better performance in low and high correlation scenarios. Please find more details, results, and discussion in our paper. We also published the code and a tutorial in the paper's repository. Thank you. Please get in touch and enjoy the rest of UbiCam.